Yeah, well, I guess I'll just wait. Oh, well, I mean, I don't want to give you like a 0.
Yeah.
We did.
Yeah.
All right, guys, it's 1:25. Let's go ahead and get started for today. So just some quick announcements up here. I released both the homework 4 and quiz, and they're both due Sunday night, same as usual. And then for the exam next Wednesday, I'll be talking about the study guide and what you might want to expect on the exam in the last 10 minutes of the class. So if I'm going over content, I get to 205 or so, and I'm not talking about it, let me know. All right. So what we talked about last time was talking about lurking, confounding variables, explanatory variables, response. And we talked a little bit about how to design a good experiment and some randomization. Does anybody have any questions from last class that they'd like to ask now? All right, so I just want to start here. I know we hit this slide last time, but I just want to reiterate why it's important to randomize. And then, so if we do randomize in these experiments, we can often determine what is cause and what effect is in this case. And so to prevent any type of biases, we want to use random assignment. And so the main thing you want to do in these cases is make sure that the explanatory variable is the only changing variable you want to look at. So you want to try to keep everything as constant and control, so you can say that the explanatory variable causes a change in the response. And then lastly, talking about the fundamental rule, you need to make sure that your data and your sample is representative to the question of interest and the larger population as well. And so why do we randomize? Well, one way we can randomize in the type of treatment is to randomly assign the treatments to the different experimental units in order to not make any biased assessments on each particular experimental unit. Another way of randomization is randomizing the order of treatments. And so I'll talk about a couple examples on how we do the order. But essentially, if 1 comes before 2, and you want to determine what's the effect of maybe 1 on 2, or even if there is an order effect, then you're going to want to randomize the order in which each person gets it. And so I know I'm a little bit glossing over this, but I'm going to show an example of each, and hopefully that helps you guys understand. So example 1, example 1 is we want to judge how fast people can go on a bike. And suppose I have one small population that is, they're very fit. And these are supposed to be little muscles over here, representing very fit people. Maybe they have a BMI of, less than 20 or something. And then we have population 2, where we have people that don't exercise regularly every day, and these people have a BMI of greater than 20. So I'm just going to have other people over here. Okay. So suppose I'm trying to judge how fast people go on a bike, and then I only test these people right here. What is that going to provide me information about? Is it going to provide me information about both populations together, or only about the fit people? Right, because if I'm taking a sample out of all these people, my sample is going to be representative to the fit people. And so if I have a type of treatment that says I have some type of steroid that I give them, and then if you don't know, steroids don't just automatically make you stronger. You have to work out and develop so they become stronger as well. And so the steroid is going to affect people in population 1 different, then it's going to affect people in population 2. And so if I'm trying to determine this steroid, do you think I should only assign my steroid to population 1 or only to 2? What do you guys think? Well, maybe. I'm actually offering a trick question here. I should have been more specific. So what you're trying to do is try and judge, how fast this is everyone, and see how well that steroid works on everyone. And so what you want to do is say get 50% of people in pop 1, 50% in pop 2, just so you have an equal representation of fit people to non-fit people, and then you split this up and you randomly assign some of them to get the steroid and some to get a placebo. And so in this case, you're going to be able to tell the differences between the populations and how the steroid affects each type of person differently. Does that make sense? Okay. So that's scenario example 1, talking about the type of treatment and you need to randomize who gets the type of treatment because it can affect one entire population different than the other ones. And then example 2 is talking about taste testing foods. And here I'm trying to get at the order. And so have you guys heard the saying that dessert ruins your appetite? That if you eat a chocolate bar before dinner, you're not going to want to eat dinner at all, or something like that. So that's what this is here. Suppose we have person A, we have A, person B, and then person C. And so person A, we have 3 foods we want to try out. So we want to try out the chocolate, we want to try out the steak, and we want to try out the rolls. And so if I give every single person rolls, then steak, then chocolate, and then this goes all the way down, they each get the same order, I'm going to be measuring something different than what I want to measure, which is, how do people like the rolls? How do they like the steak? How do they like the chocolate? Is one better than the rest? So I'm going to rate them on a scale of 0 to 10, 0 being absolutely ghastly, and 10 being wonderful, delightful to eat. And so in this case, if I only have the same order for them throughout, what they might do is say they're going to get full on these rolls, they're going to get full on the steak, and they're going to have a piece of chocolate. They're not going to like it that much because they're already full on everything else. There's no washout period going on here. And so what would be better to do is to have person A, B, C, and I'm going to assign these numbers 1, 2, 3. I put these in a random number generator, and now let's just say 2, 3, 1, 1, 3, 2, and then 1, 2, 3. Suppose this is my order. Now, because I've randomized, I'm not assessing what my order is because my people have gotten different orderings of these, so they might get full at any particular point, but I'm doing my best to not measure that. What I'm measuring is this 0 to 10 scale. And so for these treatments, which would be the foods right here, then you need to determine the right order. If there is a right order, you do that one, and if not, then you randomize it. Does that make sense? I like to eat food quite a bit. Go to Outback Steakhouse or just these other places. So this is what I think of as an example, but I'm sure you guys can think of different examples where order might matter. Maybe you think about, cereal and milk. If you're, most people think to put the cereal in and then the milk, but there's some people out there that do it the opposite way. All right, so replication and repetition. I'm gonna go ahead and erase this up here. Am I good to erase this? Okay. So we're going to talk about replication in an experiment, and then generally in science. And so in an experiment, we want to have more than one experimental unit assigned to each treatment condition. So if I have treatments A, B, and C, then I'm going to have a whole bunch of people. Just say this is my sample of people. And then I get a small portion to go to A, a small portion to go to B, and then the rest of them being assigned to C. Or more than one experimental unit is assigned to each treatment. Right. So we have multiple people being assigned to a treatment condition. You don't have just one person in A, one person in B, one person in C. You have at least two in each. And then it's large enough so, N, is pretty big for this. They have a lot of people doing this. And if it's too small, then it's difficult to draw natural variation. So us as humans, there's a lot of variation between us. And so if my sample size is small, I might measure differences between people and not between treatments. Now we have replication in science, where a single experiment rarely provides sufficient evidence for anything, and it's important to reproduce. So experiment is greater than one EU assigned to a treatment. And then this should be treatment level. Yeah. And for science, you need to have reproducible research. And if someone's not able to reproduce your experiment, you've provided a one-off case that other people aren't going to have to validify in the future. And lastly, we have these ideas between repetition and replication. And so repetition is having the same person repeat the experiment, and replication is having a different person do the same treatment or experiment. So one example of this, I'll write this over here. Repetition. And so repetition, having the same person repeat the experiment. So we're going to have person A, person B. Actually, I had treatment before. I'm going to call these different names. We're going to have Joe, Sally, and Doug as my people in this experiment. And so having repetition is saying this is experiment 1, and then they do it again, the same type of experiment all over again. And they do experiment 1, and so on. Replication is having a different person do the same treatment or experiment. So I have Joe do experiment 1, and then I have Sally do experiment 1, and then I have Doug do experiment 1. And where in this case, you have less people than you would having repeating the entire experiment over and over again. And this actually, to provide a better example, I should just use one person. So this should just be Joe with experiment 1, Joe with experiment 1, and so on. And so now we get to actually design experiments in different categories of experiments we'll be talking about. And so one specific term of DOE's is talking about control groups. And we've kind of talked about these before. These are basically the people that are compared to the treatment, and they should be about the same type of people. And the only difference is that treatment actually receives that particular drug or particular influence on them, and then control, they don't receive anything. They go along doing the same thing every day. And sometimes they get a dummy treatment, or sometimes they get the standard or existing treatment. So if you want to think about this like, maybe having some type of antibiotics for strep throat. And so if you have strep throat, maybe there's this cutting edge research that people are getting in this treatment, and then the other set of people, in order to not have an ethical problem and just let them live with strep throat, they get the normal type of antibiotics that's published by the FDA now. We also have the placebo effect and using a placebo. So it looks like the real drug, but it's no active ingredient. And so essentially what placebo is a sugar pill. So all it does is it has sugar in it, and it prevents people from taking the study and thinking, oh, well, I'm going to get this treatment anyway, and I'm going to think myself that I'm going to get better. So if you have a placebo effect, meaning that you have a treatment group, so we have treatment over here, and we have a whole bunch of people over here, and then we have the control, which will be the placebo in this case, and then you have a whole bunch of people over here. And suppose the treatment is supposed to make these people happy. And so after the experiment, we find out that the treatment people still remain the same. They're neutral right here. Where the placebo people believe they're all better and that they have smiley faces now. Maybe a little hard to see from back there, but they're smiling. And so in this case, they think that because they're receiving this treatment, it's going to make them feel better, it's going to make them happier. And so this example of the placebo effect is that these people, in theory, should just remain neutral, and the treatment people should be happy. But you've got it flip-flopped. And so whenever you encounter a placebo effect, you have to go through and repeat the study and tell them, you're thinking that this is going on. One, the experiment has just kind of failed, or two, that your drug doesn't actually work. Who here has heard of a type of blinding before, either single blinding or double blinding? A few people. So single blinding, and I think this will be easier with the picture as well. And so suppose we have participants over here. So we have participants, and then we have, let's just say we're doing a survey, and it's a survey giver. Person here, and the participant over here. In a single blind, I'm going to have them wear some sunglasses to make think that they're blinded. So the survey giver knows that they're giving this to the participant, but the participant doesn't get to see who their survey giver is or who the implementer is. So basically, they don't know what treatment. So they don't know what treatment they get. In a double blind, this is pretty simple to understand if you can understand the single blind, is that both people are blinded in this case. practitioner doesn't know what treatment they give, and the participants don't know what treatment they get. So they don't know. They don't know. And so in both of these, you have somebody behind the scenes that's basically giving them, let's just say the treatment's a box. And so I give the survey giver the box, and they give the participants that same box, but they don't know what's inside it. And then the double dummy here is that each group is given 2 treatments. So suppose you have 2 different treatments, and you have one group that gets real treatment of 1 and placebo of 2, and then you do the opposite for group 2, that they get placebo of 1 and real of 2. And so in this double dummy, you can see if there's a group effect, and then you can see if the treatment has actually worked in each circumstance. All right. Does that make sense? Does anybody have any questions on these different experimental designs? All right. So let's talk about some more for a little bit. So matched pair designs and blocking. A matched pair design is you use either 2 matched individuals, or the same individual receives each of 2 treatments. And so we talked about blocking before. Matched case design. So one is that you have 2 matched individuals, people, and then they each get the same treatment. Or 2, you have the same individual, so one person getting the same treatment, getting 2 different treatments. So if you might want to think about this, and if you're trying to evaluate physical performance again, you might want to match a 25-year-old man with another 25-year-old man, a 30-year-old woman with another 30-year-old woman, and so on, even if you're trying to do these little age groups as well. You might want to compare to people that could have different physical performance. You're not going to match a 25-year-old man with an 85-year-old man if you're trying to evaluate physical performance. And so in this case, you have to know how to match correctly. Block designs in general is where experimental units are divided into homogeneous or same groups called blocks, and each treatment is randomly assigned to 1 or more units in each block. And so the picture that I have up here, we have 3 different types of age groups. We have young, middle-aged, and elderly, which are the blocks here. And so if you think about blocks, it's the separate groups of people who are receiving each treatment. And so based on random assignment, people within each receive methods 1 and 2, and then you compare within. So you're not comparing method 1 of young to method 1 of middle-aged. You're comparing method 1 to method 2 within young, within middle-aged, within elderly. And so a special type of having blocks in different units is called repeated measures. If you have different individuals, and then you have repeated measurements on them. So suppose you're doing this study, and you're trying to understand the impact of a drug on people, and then you have like 1 day after they get the drug, 2 days, and then you go all the way to a week, so 7 days, 14 days, and then you go all the way to a month, and then maybe they follow up the year after, so 365. And if you have one person that is repeatedly being measured on this, so they get a measurement of, let's just say 10 here. They get a measurement of 8, of 3, of 2, of 1, and then 0 down here for the same person. This is an example of repeated measures. Does that make sense? Any questions out there? All right. We talked a little bit about the randomized block design, but I just want to follow up on it, knowing what we learned about randomization and in blocks. So what is the blocking factor in this randomized block design? Can anybody let me know? Gender, right. Male or female. And then you get random assessment within that, and then the treatment is the anti-anxiety drug or the placebo in this case. And then you can compare within each block to see how well they're doing on study. So I want to talk about a case study that involves a multiple of different concepts. It's case study 6.3 in your book. And so I just have it up here because I don't have it exactly memorized. But basically, you have 240 smokers. And basically, they have to be motivated to quit smoking by doing the nicotine patch. And so essentially, you have 240 smokers here, which is your sample. And then you randomly assign these to different groups. And we have group 1 where they get the nicotine patch for 8 weeks. And we have group 2 where they get the placebo for 8 weeks. And so specifically in this study, they did a double blind, meaning the people who are giving these patches to the people in this don't know that they're giving them. And then the participants obviously don't know that they're getting either nicotine or placebo patch. Can anybody let me know why it might be important to do a blinding here when you're understanding the difference between the different patches? So why would I want to blind here? Why not just like, okay, I'm giving person A the nicotine patch, person B, I'm giving you the placebo patch, one that doesn't have the nicotine in it. Yes?
You don't want to change the nurse's observations of the patient, so you don't let them know what kind of patch you're giving the patient, and the patient obviously shouldn't know what patch they have, or else they'll change their reaction to our behavior.
Right. So if a person knows that they're not receiving the nicotine patch, they're not going to be as incentivized to try and quit. They know they're just receiving a dud, and they're not going to do anything. I think, Annie, you were getting at, like, either the nurses that are applying this to people, they don't want them to give any types of clues onto what they're receiving, either a nicotine or a placebo patch. Any more questions on why this is a double blind and also placebo controlled? Because if you didn't have a type placebo here, you're going to think people are going to maybe just try and quit on their own. They want to see if the nicotine patch really does work. So any questions? All right. So now I want to talk a little bit about observational studies. So far, all of today, I've been talking about experiments, right? Where I have this treatment and I'm applying it to certain groups of people. Observational studies, if you remember, is that I'm just looking at people. So just looking at people, I don't know how to draw eyes, maybe it's like this. Where I'm just looking at people in their natural setting. This is going to be some grass going on over here. I got a smiley face and a frowny face over here. And me as the observer, I feel like it'd be a lot better if this almost just took an arc class at some point. You want to draw people or whatever. But basically, you have an observer looking at a group of people. And so one positive of this is that you're more likely to measure participants in their natural setting. So if you have an experiment, you're taking people out of their natural setting, out of their homes, bringing them to some central location, and literally testing on them. And so if that is important to understand the natural setting, then you should do an observational study. But the downside is that you can't really establish any cause and effect links. You can really only observe what they're doing, what's going on, what the relationships are, and if they're really associated. So you can't really do any type of cause and effect because there might be other variables that are influencing their natural environment. And so I'm going to talk about some types of observational studies, and the names of these are pretty explanatory into what they do. So one type of observational study is that the data is from the past. So if I just get a focus group of 20 people and I ask them to remember the happiest moments in their lives, that would be an example of a retrospective analysis, retrospective observational study. A prospective is that the participants are followed into the future and their events are recorded. So suppose I'm observing these on, let's just say, September 1st. And then I see what they're doing for a little bit, and then I look at them a couple days later. And then I go all the way down to maybe October 1st. And then I see what they're doing in their environment. Maybe they moved a little bit. Maybe they're getting closer together. Maybe they eat. Depends on what you want to measure in your observational study. Thing is that you continue to measure them into the future. Oh, geez. All right. And lastly, we have case control studies where cases have an attribute or condition. So not a treatment, but they have a case applied to them. And then they're compared to some type of control group that don't have an attribute or condition. And so one example of this is in case study 6.4. Where they have, am I good to erase this? So, case control. So in this case, we're trying to take a look at if baldness has a positive effect or negative effect on the amount of heart attacks that you can have. And so the cases in this case are people that are bald. You didn't make them be bald. You didn't give any hair remover to them or anything. They're just bald as is. And then you have people of men that are admitted to the hospital that are not bald. Oh, jeez. Actually, that's my mistake here. So it's actually the opposite way. So they're seeing if a heart attack influences how bald they are, which is a kind of pretty silly in that anyway. But just an example. And so we have this group over here in my observational study where I have 665 men that have a heart attack. And then I have 772 for something else. So if I were doing it with a heart attack here, I'm not causing the heart attack, and so I just see if they do have one. And so in this case, we have 665 men that have a heart attack, 772, and then I can see, maybe this people, they have 23% baldness, and these people have maybe 10% baldness, maybe depending on the study and with my margin of error that I calculated with this, that I can see, oh, well, yes, baldness, heart attack is associated with baldness. But you notice I didn't say heart attacks cause baldness in this case, they're just associated. right. Well, lastly, I'm going to talk about bias for a little bit. We talked about response bias and different types of biases with surveys before, but we want to talk about biases in terms of just general experiments and observational studies in general. And so there's this idea out there that is called the caveman effect. And so the only thing that we know about cavemen comes from all of the information that was kept safe on the rocks and the walls. If they wrote on any trees, or if they wrote on any type of foliage, or tried to have stories that were between people, we can't understand that part of them. And so with the cavemen, we can only understand the things that were in a cave, and then, you know, all of the other possible information about cavemen we can't see, because all that information is faded over time. And so prehistoric people are associated with caves because that's where the data is, not because most of them were in the caves their whole lives. So there might even be a case where cavemen spent most of their time outside of the cave, but we wouldn't know that because we can only see this amount of data. And so another example about potential bias is if a pollster conducts a telephone survey to gather opinions about the general population and what they think about welfare. And so in this case, my bias is that there's only people with telephones. And so I can only poll people that have telephones, and the people that don't, I can't poll. So just a little reminder that whenever you're presenting either research or results to somebody, you need to be aware of your biases before doing so. And then lastly, you decide to find out how your neighbors feel about the neighbor who seems to be running a car repair shop on the front lawn, and you place a questionnaire in every mailbox within sight of the offending home, and you ask people to fill it out and return to you. And about 50% return the survey, and 95% that they find it intolerable. So I'm just going to draw a little situation on the board so that this makes more sense. So I'm going to have a square here. This is where the car repair is. And so I do a convenience poll of all of the different houses within this. So what's one potential source of bias if I'm trying to figure out if they need to be getting rid of the car repair shop or not? Yeah.
Well, only the people that really care about it are responding.
That's right.
95% is really only like 60%, but 40% of the people don't care enough about it to actually respond.
Yeah. So first off, you get a good number of neighbors that return the survey. So, you know, let's just say these people are the ones who return the survey here. And so these are the people that it truly affects, and that's why they say 95% that think it's intolerable. So the people over here, they'll read the survey and think, well, I don't really care. They just chuck it out the window, they don't even bother to figure it out. And so the bias here is a type of response bias where the people who are responding to it are the people that it really affects. All right. Any other questions about what we've discussed so far today before we go discuss this data? All right. So the rest of these are just additional slides in here. I won't be testing about, you know, the Hawthorne effect or anything. This is just additional content if we got to it. So I might incorporate some of it next time, but this won't be tested on exam 1. All right. So so you can see this in Canvas on, it should just be in the general folder and it's labeled review for exam 1. And so first off, you should have a fully operational calculator. This should be calculator instead of computer. It said that. You need to have a fully operational calculator to take the exam. You will be allowed to have one cheat sheet or formula sheet, whatever type of information that you would like to put on that, please do. It's also a really good study skill that if you fill out this formula sheet and try to put as much information on it front and back, actually end up doing better on the exam because that helps you study and helps you figure out what's most important. So you may have a calculator with you during the exam. However, you know, traditionally, no phones, no laptop, no other electronics, you know. I don't want to see you go on your Apple Watch and type in, you know, a calculator on here. Just have one with you. And if not, let me know and I'll try and get you one. During the in-class exam, so there is going to be, so 20% is your exam 1. And then out of this, 10% is in class. And then the other 10% is a take home. And so in class, you don't have your computers. I'm not going to expect you to tell me what you would do in jump. I'm just going to ask you to try and interpret some graphs like we looked at before, some scatter plots, bar charts, box plots, that type of thing. However, in the take home, I will probably do at least 1 or 2 jump problems in there that ask you to make some type of graph and interpret it as well. Unless you receive accommodations from the SSD, you'll have 50 minutes to take the exam. So at 1:25 next Wednesday, I'm going to start it, and then you'll have until 2:15 to turn it in. From there, like I said, it's worth 10% of your final grade. We have an out of class that covers 10%, and you can go back and forth between questions, of course, as well. So just the types of topics that we'll be discussing on exam 1. I'm not going to talk about all these here, but generally it's going to be chapters 2, 3, 5, and 6. There's a little bit on 4 that examines categorical to categorical relationships, and that's just in plotting and stuff like that I've included on the slide. So I think part of it is also 4.1 as well. And so I'm going to be asking you specifically, you should be able to calculate a mean and variance/standard deviation on the exam. I'm definitely going to be asking you how to do that at least 1 point on the in-class exam. So make sure you know how to do that. Make sure you know what explanatory and response variables are. I may have a question on the empirical rule and the standard normal curve, just meaning, you know, what the z-score is, x minus mu over sigma. So just giving you some hints of what you could possibly include on your formula sheet. You could also include like a picture of your graph that you had before, and then the conclusion that I have on the answer sheet or whatever that helps you interpret what a scatter plot is, what a bar chart is, and so on. So basically, know how to interpret charts, know how to interpret scatter plots, correlation coefficient, coefficient determination, know what these are. And then about sampling methods, you need to know the different types of sampling methods that we've had before. So simple random sampling, stratified, cluster, and so on. Different types of bias, I encourage you to know. And then what we've talked about the past couple days, experiments and observational studies, and then these specific ones. So if I tell you, you know, this is the problem, you need to go identify what type of design I would use in that case, and why would I want to use that one. And lastly, talking about lurking variables and confounding factors, along with I talked about the end, randomization, and then replication or repetition in science experiments. Alright. So that pretty much covers it. This is a complete list. I'm not going to have a question that doesn't touch on something that is talked about here. So yeah, are there any questions about the exam? Yes?
Yeah, what's going to be the format, like all of them choice and
Yeah, there's going to be some multiple choice, some type of like, give me a statement or two, some type of short answer. And then I may have like a fill in the blank. Yes? It'll be due the Sunday following. Yeah. You can include anything you want, as long as just one sheet front and back.
How many questions in class?
I'm not sure yet. But it's going to be enough for you to take in 50 minutes. Any other questions?